Assalamualaikum. We are from Group 5C and we are going to present about production of LDPE, HDPE and LLDPE. The group members for these presentations are me, Nur Hannah binti Mohd Mokhlis,
Nurul, Hafawati binti Rosdi,
Farra Batrisyia, Zaiba binti Zuhaire,
Nurfarah Nadhira binti Mohamad Bisri,
Norazila binti Mohamad Shamsudin Kiong.
This is the content that will be presented in this slide. First, introduction of polyethylene. Polyethylene was first synthesized by the German chemist Hans von Pechmann, who prepared it accidentally in 1898 while heating diazomethane. When his colleagues Eugen Bamberger and Friedrich Tishner characterized the white waxy substance he had obtained, they recognized that it contains long CH2 chains and called it polymethylene. The first industrially practical synthesis of polyethylene was in 1933 by Eric Fawcett and Reginald Gibson at the Imperial Chemical Industries ICI in Northwich, England. Because the reaction had been initiated by trace oxygen contamination in their apparatus, the experiment was at first difficult to reproduce. It was not until 1935 that another ICI chemist, Michael Perrin, developed this accident into a reproducible high-pressure synthesis for polyethylene. That process became the basis for industrial production of LDPE, beginning in 1939. In 1953, German chemist Carl Ziegler developed a catalytic system based on titanium halides and organoaluminium compounds that work at even milder conditions than the Phillips catalyst. The Phillips catalyst is less expensive and easier to work with. However, both methods are used in industrial practice. By the end of the 1950s, both the Phillips and Ziegler type catalysts were being used for the production of HDPE. A third type of catalytic system based on metallogens was discovered in 1976 in Germany by Walter Kaminski and Hajan Sin. The Ziegler and metallogen catalyst families have since proven to be very flexible at copolymerizing ethylene with other olefins and have become the basis for the wide range of polyethylene resins available today, including very low-density polyethylene (LDPE) and linear low-density polyethylene (LLDPE).
Moving on to the production process. Polymerization reactions. Polymers are high molecular weight compounds formed by the aggregation of several smaller molecules called monomer. The plastics that have changed nature and the natural and synthetic fabrics used in clothing are polymers. There are two basic ways of forming polymers. The first one is connecting small molecules together is a type of addition reaction as known as chain growth polymerization. And the second one is combining two molecules of the same or different type with the removal of a stable small molecule such as water. This latter type of polymerization combines addition and elimination reactions and it is called a condensation reaction or step growth polymerization. So the first one is chain growth polymerization. Chain growth polymerization is a process in which the high molecular weight polymer is formed early in the polymerization process and the yield of the polymer is gradually increased over time. Addition reaction. Chain growth polymerization is a chain reaction that adds new monomer units to the growing polymer molecule one at a time through double or triple bonds in the monomer. For example, molecules of ethane can polymerize with each other under the right conditions to form the polymer called polyethylene. The reaction above show the basic steps to form an addition polymer. The first one is initiation step. It is a free radical initiator attached to carbon-carbon double bond and then the initiator can be something like hydrogen peroxide. The second step is propagation and the last step is termination. Polyethylene can have different properties depending on the length of the polymer chains and on how efficiently they pack together. The next one is radical and coordination polymerization. It is assembly of linear macromolecules supports the named chain growth polymers. Since a pi bond in the monomer is converted to a sigma bond in the polymer, polymerization reaction is usually exothermic. It is useful to distinguish four polymerization procedures fitting the description of radical polymerization. The first one is radical polymerization, cationic polymerization, anionic polymerization, and coordination catalytic polymerization. Radical polymerization. When radical polymerization is required, the use of a radical initiator such as peroxide or certain ozone compounds must begin. One example of this radical polymerization is the conversion of styrene to polystyrene. In initiation step, each monomer unit adds to the growing chain in a manner that generates the most stable radical. Propagation step is very fast and a long polymer chains will be formed in the earlier stage of the reaction. Termination can occur by disproportionation or recombination. Since carbon radicals are stabilized by substituents of many kinds, the preference for head-to-tail radioselectivity in most addition polymerizations is understandable. As in case of disproportion, the final polymers are on average of the same length as the growing chains. Termination occurs by transferring the hydrogen atom from one radical to another, leading to unsaturation at one end of the chain. Recombination results in polymers with an average of twice the length of the expanding chain. It involves moving the radical end of the expanding polymer chain to another species, such as a monomer or a solvent molecule. Chain transfer decreases the average size of the polymer and the molecular weight. Thus, by adding a chain transfer agent to the modifier, the average degree of polymerization can be managed. When polymerization is carried out in the solution, the solvent will act as a chain transfer agent, and as a result, when the solvent is not in it, the average chain length will be small. Side chains are also produced by an internal chain transfer in the production of low-density polyethylene, LDPE, with coordination polymerization. Metal catalytic converters are normally involved. The most common catalysts are the so-called Ziegler-Natta catalyst and the Phillips catalyst, both of which were discovered to be efficient for alkene polymerization in the 1950s. The formation of bonds between one of its carbon atoms and the metal and between the other carbon atom and innermost carbon atom of the current chain inserts a new ethene molecule. High-density polyethylene HDPE is formed from this type of polymerization. When propene is used as a polymerization feedstock, polymers with very different properties may be produced depending on the microstructure of polymer chain. Structure of the propene polymer determines the properties of the material to a large degree. The polymer chains would grow very long on the Ziegler-Natta catalyst. Therefore, a chain transfer agent is added to the system. The most used hydrogen is the donation of a hydrogen atom to terminate and detach the chain from the metal atom. Step growth polymerization. A stepwise reaction between bifunctional or malfunctional monomers in which high molecular weight polymers are formed after many steps. In contrast to chain growth, all monomers are reactive. Therefore, most monomers are consumed early in the polymerization to form short chains, oligomers that combine to long polymer chains in a later stage of polymerization. Condensation reaction, a form of step growth polymerization in which two molecules combine, usually in the presence of a catalyst, with elimination of water or some other simple molecule to form large structural units. The combination of two identical molecules is known as self-condensation. Catalysts commonly used in condensation reaction including acid, bases, the cyanide ions, and metal ions. A classic step growth condensation is a reaction between a dibasic acid and a glycol. The resulting polymer is called a polyester. The water is continuously removed from the reaction system because it is reactive with ester linkage to reverse the reaction. One of the most common thermoplastic polyester is polyethylene terephthalate, often abbreviated as PET or PETE. Both nylon and PETE do not need a catalyst because the acid monomers to catalyze the reaction. However, strong acids such as sulfuric acid further accelerate the reaction. They have the advantage that there is usually no reversal reaction. Long short story, this is the difference between addition and condensation polymerization.
Moving on to the process equipment used in LDPE process. The first main equipment used is stirred autoclave reactor, or known as CSTR. CSTR consists of a stirred autoclave with a cylindrical vessel with a length over diameter ratio of 4:1 to 18:1. The reactors for large plant usually have volume of 1 meter cube and residence time of 30 to 60 seconds. The reactor wall thickness is usually 0.1 meter to contain the high pressure of the process, which is around 2100 bar. The wall thickness severely limits the heat removal, therefore the only way to release heat produced in this reaction is by the fresh cooled ethane entering the reactor. CSTR operates adiabatically with a very high temperature and pressure. The conversion is limited to around 20% to limit temperature increase and to avoid local hotspot caused by difficulties in stirring as the viscosity increase along with the high polymer content. The first zone of reactor usually operates at 490 Kelvin and in the final zone operates at 570 Kelvin. The initiators are injected at several points along the reactor to start the process of polymerization. Every 4 zones of reactor are separated by a solid disk type structure that will rotate with the agitation impeller. Basically, it works as zone separator as well as agitation device. The second main equipment is tubular reactor, or known as PFR. PFR operates at high temperature and pressure just like CSTR. Tubular reactor is basically a long double pipe heat exchanger. The industrial reactors have a length of between 200 to 1000 meter with inside diameters of 2.5 to 7 centimeters. It is built by connecting straight length of 10 to 20 meters in series with U-bends. The tubes are surrounded with jacket as it is part of heat transfer process. The feed for this process, which is ethane, is heated at 370 to 470 Kelvin in the first part of the reactor. The process of polymerization inside the reactor will then raise the temperature to 520 to 570 Kelvin. The initiators such as oxygen or peroxide are injected at several points of the reactor to start the polymerization to form polyethylene. Initiators will increase the conversion. However, the increased number of initiators will also increase the reactor length. Single initiator injection could produce ethane conversion ranges from 15 to 20%, while multiple initiator injection could produce up to 35% ethane conversion. The cycle valve, which is located after the reactor, is to control the velocity for effective heat transfer to the cooling jacket by opening the valve sometimes to reduce pressure to around 2000 bar. The advantage of the valve is to reduce contamination of the walls with polymer as the flow velocity increases sometimes. But the disadvantage of the valve is the tubes have to endure both large pressure changes and the temperature gradients through the walls. Recycle stream is required both in autoclave and tubular reactor as the conversion of ethane is low. The two types of separator inside the process. High pressure separator will separate most of the polymer from unreacted monomer. The overhead stream contains ethane and other low molecular weight polymer in forms of waxes. The waxes are then removed and the ethane is cooled in order to recycle back to the reactor. The bottom stream feeds to low pressure separator. Low pressure separator is where most of the remaining ethane monomer is removed. The overhead stream contains ethane that will be recycled back to the reactor. However, some will be purged to prevent accumulation of feed impurities. The bottom stream will be fed to an extruder. The product will go through multi-hole extrusion process where it is forced through a die with multiple holes. The pelletization process will then cut the polymer strands from the extrusion process of about 3 mm diameter and it is dried in a centrifugal dryer.
Next is the compressor. Centrifugal compressor solely is not adequate to create enough pressure required in LDPE process. The maximum discharge pressure around 1000 bar at lowest flow rate is insufficient. Therefore, reciprocating compressor is needed as well in the process. Centrifugal compressor, or known as primary compressor, used to increase the pressure of ethane to 300 bar. Reciprocating compressor, which often known as hypercompressor, is then used to increase the pressure to 15,000 to 3,000 bar.
Next, we move to the process equipment in HDPE and LLDPE process, the fluidized bed polymerization reactor. The height of the reactor is around 25 meter and the length to diameter ratio is about 7 to 15. It consists of cylindrical reaction section and larger diameter section which have lower gas velocity. Thus, the retained particle repel back to the bed. The residence time of the catalyst particle in the reactor range from 3 to 5 hours during their average size of 500 micrometer. In the fluidized bed polymerization reactor, the ethane, hydrogen, and comonomers such as 1-octane, 1-hexane, and 1-butane are fed at the bottom of the reactor. The catalysts are fed nearly at the top of the reactor and usually use a titanium tetrachloride and chromium oxide. As the catalyst move downwards, the polymerization process occurs. The polymer grows on the catalyst particle will increase its width and size. Therefore, the heavy polymer particle will move downward toward the base of the reactor where the product stream is located. The light particles, which are the non-reactive gas, will leave the reactor and can be recycled back to the feed. There are two main reasons why pre-polymerization CSTR exists in the industrial process. First, the pre-polymerization catalyst particle will decrease the reaction activity in the catalyst feeding section, which leads to the lower temperature throughout the reactor. This can prevent the formation of hot spots inside the reactor, polymer melting, and the reactor shutdown. Second is to produce specific polyethylene grades. In pre-polymerization CSTR, the ethane, hydrogen, and comonomer are fed to the reactor along the catalyst, which produce pre-polymer. The pre-polymer is then fed into the fluidized bed reactor to complete the polymerization process. The remaining polymer particles are being separated from the monomer in the cyclone and being recycled back to the fluidized bed reactor. The remaining ethane from the polymer will push along with nitrogen and stop. There are no residual catalyst removal unit as the process high activity of polymerization process where the production are based on the catalyst used. The single pass conversion of ethane is around 2%, which cannot be higher by using higher comonomers. The temperature control is very important in this process to prevent thermal runaway reaction and keep the polymer below their melting point. For HDPE, the melting point is 398 Kelvin and LLDPE is 373 Kelvin. If thermal runaway reaction occur, carbon dioxide can be used by injecting it into the reactor to poison catalyst and so the reaction could stop. Next, we move to application of LDPE, HDPE, and LLDPE. LDPE is used for plastic wrap, computer hardware packaging, juice and milk packaging as a waterproof inner and outer layer, six-pack ring, playground slide. Next, HDPE is usually used to form a chemical drum, sturdy bottles, bottle trays, toy and polyground equipment, picnic wear, household and kitchenware, cable insulation, carrier bags, plastic mailing envelope, flexible HDPE pipes, and monoblock chair. For LLDPE, it's used to form a film, plastic bag, scratch wrap, pouch, toys, lids, covers, pipes, buckets, and container, and lastly for the covering of tablets.
Alright, next I will proceed with the diagram example of LDPE, HDPE, and LLDPE. First, this is the diagram example of LDPE, HDPE, and lastly LLDPE. I will proceed with the video elaboration. For the first video, the title is LDPE versus HDPE, similarities and difference. And based on this video, first it tells us what is polyethylene that can be categorized into several subcategories based on the molecular structures. And then it tells us the similarities of LDPE and HDPE based on the properties. LDPE and HDPE, the low material weight and low manufacturing costs based on the employed in injection molding operations. LDPE and HDPE have the fastest injector speed. Next, it tells us the similarities of HDPE and LDPE have led to the similar applications. Next, it tells us the differences based on the physical characteristics. LDPE is softer and more flexible than HDPE, which was rigid and durable. It offers a greater chemical resistance. Based on the recyclability, both are recyclable but classified with different recycling number. This is the video low density polyethylene. This is the presentation of on LDPE. And next, material minutes, high density polyethylene by the medicine group. It discussed and dissect the polymeric material HDPE utilized to make the product. Next, this is from a video from natural gas to plastic. It tells us how LDPE is produced from natural gas to plastic. And lastly, it is LLDPE video tell us the manufacturing process of LDPE and how the plant works. Then I will proceed with the top polyethylene company. First, we have Lotte Chemical Titan, which located at 3 places. First, wilayah Persekutuan Kuala Lumpur, Pasir Gudang Johor, and lastly at Georgetown, Penang. Lotte Chemical produce Malaysia's most comprehensive portfolio of olefins and polyolefins. Next, we have ExxonMobil Chemical, which located at Mineral ExxonMobil Kuala Lumpur. This is the one of the largest chemical companies worldwide. Next, the Petronas, the Etepec Company, which located at the Nilai Negeri Sembilan. And lastly, we have GT Max, which located at Klang Selangor. All these companies provide LDPE, HDPE, and LLDPE products, also with other plastics products. That's all from me. Thank you.